And our speaker is Jong-Hak Woo, a professor at Seoul National University in Korea. So he will talk about the black holes. And Jong-Hak, could you share your screen?
Sure.
You will have 20-minute talk followed by 5-minute Q&A. And Jamika will be notify you when there are 2 minutes left. You will see the stars on your slide, very small stars. So watch out that star. And okay, it looks good. Yeah, you can start.
Okay, all right. Sorry. Let me just use the spotlight. It doesn't go away. Okay, so thanks for the introduction. First of all, I'd like to thank the organizers for inviting me to present my science work. My talk title is slightly changed, but it contains the take-home message, so please take a look. The main topic is the agent feedback on star formation. So after giving you some backgrounds, I will present the highlights from our demography study of outflows and star formation, and then from IFU studies. So the first question is that why we want to study AGN feedback. The first motivation comes from the black hole galaxy coevolution paradigm. I see it chatting. Okay. So for example, we know that black hole mass correlates with the host galaxy properties. And for example, here is the M sigma relation, the black hole mass versus stellar velocity dispersion relation. A popular interpretation of this correlation is that there must have been some sort of self-regulation between black hole growth and galaxy evolution. On the other hand, it's also possible that simply big galaxies host the big black holes without self-regulation. I'd like to show you one plot here, which is the intermediate mass black hole in NGC 4395, which is a dwarf galaxy, and we try to measure the black hole mass based on reverberation mapping. And this intermediate mass black hole and galaxy seems to follow the M sigma relation of supermassive black holes. This galaxy presumably didn't go through a major merger or energetic AGN phase. If this is the case, then the M sigma relation may not require the self-regulation or AGN feedback. So I would say the nature of the correlation is unclear, at least at the intermediate or the low mass, intermediate black hole mass regime and the low mass galaxy regime. The second motivation comes from the cosmological galaxy evolution models. So we know that the lambda CDM model predicts too many massive galaxies compared to the observed luminosity function. And perhaps AGN play an important role by suppressing or quenching star formation in massive systems and resolve this discrepancy. So these days, cosmological models routinely include the AGN feedback to reproduce the observed galaxy properties. However, I would say we still need to have a smoking gun observational evidence of AGN feedback on the star formation. So now, gas outflows are probably the main channel of the AGN feedback. So in this talk, by AGN feedback, I mean the regulation of star formation. We know that gas outflows at the large scales, 10 kiloparsec scales, and we also know that for individual galaxies, there's evidence of suppression and the triggering of star formation, and sometimes both for a given galaxy. So here is an example of positive feedback, the NGC 5728, as based on my former student, Jie-Jin Shin. So this galaxy has a biconical outflow, AGN outflow, and also it has a star-forming ring at the center. So what happens, we think, is that the outflow encounters the ring, and then the compressing ISM and triggering or enhancing star formation. So if we see the H-alpha map, then basically at this encountering area, we see very high star formation rate, but in contrast, we see the lack of CO gas. So very high star formation efficiency, indicating probably the positive feedback. So now, although we have detailed studies of individual galaxies, we still need to have a good demography study of agent outflows and star formation to unveil the nature of the agent feedback. So the key questions are: the first, energetics, how much mass can be carried out by outflows? This is very uncertain. Secondly, what would be the overall impact of the feedback on global star formation? This is very complex. We actually need to have a spatial information to answer this. Third, what would be the timescale of the feedback, whether the suppression of star formation is instantaneous or in a short time scale, or maybe it takes a long time to see the decreased star formation rate after agent activity. So these are still remaining key questions. So my group at Seoul National University have been studying outflows over the last several years. First, by focusing on the demography of outflows and their impact on star formation. And secondly, they're based on the integral field spectroscopy data. So I will try to make several points from these studies. First, the outflows and their impact on star formation. We've been building up a large sample of type 1 and type 2 AGNs and a comparison sample of star-forming galaxies based on BPT classification and based on the broad emission line identification. For their star formation rate, we are using far infrared luminosity as a star formation rate indicator. But all sky surveys are typically very shallow in far infrared. So we also use the infrared luminosity estimates based on artificial neural network analysis from Sarah Ellis in 2016. So I'm not going to go in detail, but when we compare the star formation rates from these two methods, we get a consistent star formation rate. We also use the SDS-based infrared luminosity, but this applies only several tens of objects for consistency check. So to trace the ionized gas outflows, we are mainly using action 3 line, which typically shows two components. The narrow core component in red represent the gravitational potential of the host galaxy. But we see the very broad wing component, which is in blue. So that is due to the agent outflows. So using this line profile, we measure first and second moment and determine the velocity and velocity dispersion of the gas to quantify the kinematics. So we think that these outflows are biconical shape with the hollow cone and partly extincted by dust in the stellar galaxy disk. So as you can see, sometimes we see blue shifted action 3, or sometimes we see red shifted action 3 line in the flux weighted Sloan spectra, depending on the orientation. So the first message is that these outflows are clearly driven by AGN, not by star formation. When we compare AGN with star-forming galaxies in this velocity dispersion diagram using action 3 line, we see a dramatic difference in their distributions. For example, AGN has a very high velocity dispersion, and it means that action 3 line is very broad. On the other hand, the star-forming galaxies have a very, very narrow action 3 line, so it's this clear distinction. So these kinematics of the outflows are clearly driven by AGN. Now, we can ask what fraction AGN has the outflows. The answer is that if you look at the high luminosity, then almost 100% of AGN shows the signature of the outflows. When we go to low luminosity, the outflow fraction is somewhat much lower, but probably this is due to the detection issues. Since the weak broad wing is very difficult to detect, so the outflow fraction we are measuring is relatively small. But if you have a deep enough observation, we probably find the signature of the outflows even for low luminosity AGN. Now, when we compare the luminosity with the outflow velocity dispersion, we find the positive correlation. So this is not unexpected. The higher AGN luminosity, we find out stronger outflows. But for given AGN luminosity, if you see here, then there is quite a large range of velocity dispersion. So this means that there must be some other controlling parameters, such as gas fraction or density distribution, etc. However, the main driver of this outflow is the luminosity of the AGN. Now, I'd like to show you a key slides, the two key slides, and this one and next one. When we compare star formation rate with the action 3 velocity dispersion, we find a positive correlation instead of a negative correlation you may expect. So here is a specific star formation rate of type 1 AGN in blue and type 2 AGN in red. And the horizontal gray area is the main sequence and 1 sigma distribution of non-AGN star forming galaxies. So, and in x-axis, I'm showing you the action 3 velocity dispersion normalized by stellar velocity dispersion. So if you go to the right, it's a strong outflow. To the left, it's a weak or no outflow. So when we look at the AGNs with the strong outflows in the right-hand side, they tend to be above the main sequence. So this means that there's no quenching. We don't really see suppressed star formation rate. Instead, we see high star formation rate, even higher than main sequence. So this might be, there might be extra triggering of star formation due to AGN outflow. So it might be a signature of the positive feedback. On the other hand, if you look at the AGN without outflows, then they tend to be below the main sequence. So we don't even see the outflows, but star formation rate is much lower than the main sequence star forming galaxies. We have to explain why. So one scenario is that there was AGN activity and strong outflows, and they started impacting on the star formation, but only now we are able to see the decreased star formation rate. So this is the negative feedback, but it's a delayed negative feedback. If you look at the distributions of the specific star formation rate of AGN, type 1 AGN blue and type 2 AGN red compared to the specific star formation rate distribution of star forming galaxies in black, we also see the same trend. If you go down from strong outflow to weak outflow and no outflow AGN, we clearly see the decrease of the mean specific star formation rate, indicating the negative feedbacks happened some time ago. We performed the same analysis with the Eddington ratio. Again, in x-axis is Eddington ratio and y-axis is a specific star formation rate. And the horizontal area is the main sequence star forming galaxies. Now, if we look at the high Eddington ratio AGN, again, we don't see suppressed star formation rate and no quenching, but instead we see enhanced star formation rate. So AGN may have triggered more star formation rate for these objects. On the other hand, if you look at the low Eddington ratio AGN, they tend to be below their main sequence with the lower star formation rate. So this is again, we can say that maybe some time ago, there was a strong outflow and an AGN and started impacting on the star formation rate, but only now we see this suppressed star formation rate. And so this is the delayed negative feedback scenario. Distributions of specific star formation rate show the same thing in different ways. So if you go down to lower and lower Eddington ratios, you can clearly see the discrepancy between the galaxies, which is black, and the AGN in red. So in one hand, we have AGN with a strong outflows and high Eddington ratio, and these AGNs are hosted by highly star-forming galaxies. On the other hand, we have AGNs with a no outflow and low Eddington ratio, but these agents are hosted by galaxies with a very low star formation rate. So if you combine these two populations as a time sequence, then maybe you get the picture of delayed feedback scenario. So initially, agent outflows start impacting on ISM and perhaps enhancing star formation rate. But only after some time scale, we are able to see the decreased star formation observationally. So suppression of star formation cannot be directly or detected instantaneously because there's some time delay. And since there's no quenching, we cannot really get any observational evidence of suppressed star formation rate when AGN is very active. Okay, so I will move to the second part and show you some highlights from our IFU studies. So we've been observing type 2 AGN out to redshift 0.1 using various telescopes and instruments, but I will give you some highlights from the study based on Gemini GMOS IFU. So these are the optical images of the targets we observed out to redshift 0.1. They look like a typical star-forming galaxies, although they have a strong outflows. The blue box indicates the field of view of the GMOS IFU, covering several kiloparsec scales. Now, at each spectrum, we measure and we fit the emission lines and measure velocity dispersion of gas kinematics. And here is an example of the velocity map in the left and the velocity dispersion map in the right. Based on action 3 line, they show strong outflow signatures. And if you look at the central part, the action 3 velocity dispersion is very, very high. So this is clearly the agent-driven outflows. Now, one unique thing we did in this analysis is that we measure the size of outflow based on spatially reserved data. So for example, here as a function of distance from the center, we see that the velocity dispersion of action 3 decreases, and at some point it becomes comparable to the stellar velocity dispersion. So beyond which we don't see any outflow signature. So by defining the edge of the outflow, we can measure the size of the outflow and use it for the outflow energetic calculations. So I'd like to point out that this outflow size, the kinematically measured outflow size, is typically smaller than the photoionization size, the size of the narrow line region. So if you want to calculate the outflow energetics, we have to use the proper size, the outflow size, instead of the photoionization size. Otherwise, we will substantially overestimate the AGN energetics. Now, if we compare these kinematically measured size with the luminosity, that we find the positive correlation, which is not unexpected. Basically, more luminous AGN have a larger outflow size. But if you look at the physical scale of these outflows, you may be disappointed. So here is about the 5 kiloparsec scale, and the majority of our sample has a relatively small outflow scale. So here the sample is that the blue are the AGNs observed with the GMOS. Our studies plus other studies in the literature combined with the other sample based on SNP's IFU with the Hawaii 2.2 telescope data. So basically, the main message here is that these outflows are confined within the center of the galaxy, and they probably do not make a strong impact on the large disk scales where probably the star formation is still ongoing. So if you apply this correlation to general population of the AGN, then we probably don't expect to see very strong major impact on the global or the total star formation rate, because the outflow impact is rather confined at the center. So this is my last slide. We typically see the inside-out structure based on photoionization analysis. So we can classify the source of the photoionization either by AGN, red, or by star formation in blue. At the central part, it's clearly dominated by AGN. It may or may not suggest a negative feedback. But interesting thing is that at the edge of the AGN, we see a ring-like structure in many objects. A ring-like structure of star formation in many objects. So gas is not completely expelled, and there's still star formation ongoing. Interestingly, the location of the ring is comparable to the edge of the outflow in kinematical analysis. So what we think is that maybe outflow slows down by compressing ISM and enhancing or triggering extra star formation at this region. So there might be positive and negative feedback that together for a given object. So what would be the overall impact of outflows on the star formation, global star formation? Probably this is rather limited because first, the outflows are confined at the central part, and secondly, there's also positive feedback. So here's my summary. Basically, at low redshift, we find no evidence of instantaneous quenching because we see a positive correlation between AGN activity and star formation rate. Although, nevertheless, we see the low Eddington ratio AGN with the no outflows, they have a much lower star formation rate than main sequence. So there must have been some sort of AGN feedback in the past, and we now only see the decreased star formation rate. A few follow-up studies show that the outflow is confined in a relatively small region, and the star formation is ongoing in disk, suggesting a limited impact on global star formation rate. So I will stop here. Thank you.
Thank you for your presentation. And I will take questions from the Q&A. So, Janice, the question from Janice, do you have constraints on how long the star formation will last in the galaxies with strong AGN outflows? For example, gas depletion timescales?
That is a very good question, but we don't have any data to answer that question. But the time scale for depending on the star formation rate indicator, we see different time scales. Since our star formation rate is based on far infrared or infrared, maybe we are looking at 10 to the 8 year time scale. So depending on when the previous strong AGN activity happened in the past, time scale may be different, but I cannot really answer that.
Okay, next question is from Jennifer Lott. Do simulations of AGN feedback make predictions about specific star formation rate versus outflow activity? How do they compare to your result?
Sorry, I cannot really see the Q&A, but can you repeat the last part? Specific star formation rate and?
Specific star formation rate versus outflow activity?
Outflow activity. Well, I'm not really doing the simulations or the semi-analytical models, so maybe I'm not qualified to answer that. But I think most of the cosmological models include AGN feedback. But what I heard is that the quenching is not really instantaneous. But I do not know whether the outflow rate versus the specific star formation rate is well constrained by the models. Did I answer that question? I'm not sure.
And the question from Joel. Should we conclude from your results that galaxies evolve along the relations between AGN activity and specific star formation rate throughout the AGN duty cycle?
I think not. While I think the AGN play maybe significant role, but in my opinion, it's probably this impact of AGN outflow or feedback be rather limited based on the relatively low redshift study. But if you look at the high redshift, probably the environment is very different. So maybe agent feedback is very important, and the duty cycle is very important. But at least at low redshift, we don't see any strong evidence for that. Even at high redshift, theoretically, we can imagine this AGN role, but I think still we need to have smoking gun observational evidence of AGN feedback on star formation and regulation of star formation.
And thank you. And I have a question. Since you studied both type 1 and type 2 agents, so is there any difference between stellar mass on type 1 and type 2 agents?
We are using the small sample mainly for the demography study, and I think they are somewhat different because we are using the galaxy catalog for type 2 AGN and try to select the type 2 AGNs. For type 1s, we are using the quasar catalog. So the stellar mass range is slightly different, but since we are using the normalized star formation rate, the specific star formation rate, probably that doesn't affect the main result we have.
Okay, thank you very much again. And we are running out of time. Please continue the discussion on the Q&A. And now there are chat sessions with speakers. So please go ahead directly to the Zoom link. And thanks again for all the speakers today for their discussion and presentations. I guess this is all for today. And thank you everyone for joining today, and I hope to see you all again tomorrow. Mahalo and bye-bye.
Thank you.